Good evening, everyone, and welcome to the Week 8 live session for the course Deep Learning for Computer Vision, conducted by Professor Vinithin Balasubramanian. So, my name is Aveen Dayal. I'm a PMRF PhD scholar at IIT Hyderabad. I'm in my final year of my PhD, and my research area lies in deep learning techniques, developing robust deep learning techniques for mostly autonomous systems like self-driving cars, autonomous drones, etc. So coming to the course, up till now we've discussed. I think we are in week 8. So previously we started off with traditional computer vision algorithms. Then we moved into more deep learning based computer vision algorithms, like how we can use MLP. Like we understood what MLP working is and how we can uh, create such neural network architectures and what are the different tasks or problems we can solve with that. Then we came across, then we move forward to convolution neural networks. And so we clearly contrasted between why convolution neural networks are important and how convolution neural networks are much better than MLPs, especially for image modality. This is because in images, typically we have this assumption, fundamental underlying assumption about spatial invariance or some inductive bias. Like if an object is present in one spatial locality of that image, wherever the object is present, that object still remains the object. Like, for example, if a car is present at the top left of the image, so we as humans know that okay, the car consists of certain structure, like small patch of the local region around that particular car is on a certain structure, like wheels are at the bottom, then the window is in front of the car, the bonnet is in certain direction, etc. Now, similarly, if the car is again shifted somewhere else, probably towards the bottom right of the corner or anywhere else, also, we still know that's a car because we always look at the nearby pixels and we draw inferences based on these pixels. So, such type of biases is what typically human brain uses. So, we try to instill the same type of inductive biases for the neural network architectures also, and that is what CNNs were developed, and they do very well at these tasks. And then we started looking into more complicated tasks other than simple image classification. We moved forward to more complicated tasks like object detection, where the goal was to not just classify what particular class the image belongs to, but also understand where that particular object is present in the image. So what we typically call is drawing a bounding box across the object. Then we moved on to semantic or instance segmentation, where segmentation as a concept is nothing but classifying each pixel into a particular class. So image classification is classifying the entire image into one class. Segmentation is classifying each pixel into a separate class. And then the difference between semantic and instance segmentation was, in semantic segmentation, we don't differentiate between different instances of the same class. Like, for example, if you give a color of blue for a dog, two dogs in that particular image will be given the same color. Whereas in instance segmentation, each instance of the class is also given a different color. So, dog 1 will be given blue, dog 2 will be given a different color. So, where is it needed? For example, there are a lot of applications where um, typically, I think this was one of the examples where during COVID time people wanted to do crowd monitoring, whether a lot of people were there touching different surfaces and all those things. So in that particular instance, people try to develop these algorithms, instance segmentation, not for images but for videos per se, and it is slightly into object tracking also, where they try to understand what whether typically people who are interacting with each other are they maintaining the distance and all. So if you think about it, if you consider all the people as one particular group, it might not really differentiate who is doing what. So we want different people to have different instance or different color coding to understand that okay, person one is doing behaving in certain way, person two is doing in certain other way. Typically, in other examples, also you can understand if how instance segmentation is needed or can be advantageous. Then we moved into slightly tangent, where we tried to talk about sequence to sequence models or RNN models called recurrent neural networks. So recurrent neural networks, they again have their own set of biases when they were being developed. in RNNs, the bias is that the input modality is typically a sequence. What is a sequence? Like if you consider videos is nothing but a sequence of images, image frames. Or if you want to think about sentences or text paragraphs, right? Each word, a paragraph is nothing but a sequence of different words, or a document is nothing but a sequence of different words, pages, etc. However you want to define it. Now, to model that, we can't use CNNs directly, because CNNs, like I said, when they were fundamentally built, they were with an assumption that the inductive bias and all, but there was no assumption of CNNs where they can handle sequence to sequence data. All CNNs do is take one particular image at a time and give some output. But there is no way that CNNs can identify what is the relationship between one image frame and the other image frame, because they are not developed or modeled such way. That's where RNNs are helpful, and that's what we saw in the last class. Um, Different types of recurrent neural networks, like uh, LSTMs, long short term memory networks. Then there are GRUs called gated recurrent units. And we also saw the difference between LSTMs and GRUs. There are differences are typically based on the number of gates, the computational complexity, um, and whether they have the memory state or not. Then finally, we I also gave you some idea about what are the fundamental problems in all these RNN models. Is that they what to say, they model the sequence to sequence data in a sequential manner. Like for example, the input is a bunch of words, right? So the model first takes the first word, then it takes the second one, then it takes the third word, and so on. While this is good for shorter sentences or small input sequence data, but when we keep on looking at bigger and bigger sequence data, like for example a book, for that reason, like a book consisting of 20-30 pages, then this won't help, because typically these RNNs will forget the starting tokens or words when it is looking at other different ending parts of the input data. So this is the long context problem, which we usually call. So RNNs fundamentally are not very good at very long context problems. That is one issue. And the other issue is also mm, the representation learning. While they're very good, it comes with a lot of other problems of forgetting and etc. Even after using gates. No, I'm not talking about typical RNNs, the vanilla RNNs. I'm talking about even after using LSTM gates and GRU gates, this problem of forgetting and all those things still happen. And that is where today's week content will come. That is the attention modules and transformer architectures, which is nothing but built on top of the attention module itself. Yeah. Before that, also, while we looked at the models aspect, we also in this week 8 we talked about the applications of the sequence to sequence model in computer vision. So one was something called as image captioning. So image captioning is nothing but, if you had an image, and let's say in this particular image we had a boy playing with a ball, like he throws the ball, let's say. So we ideally give this particular image as an input to the model. Now this is nothing, this typically consists of CNN plus some type of sequence to sequence model, RNN. And we ideally want a textual description of this particular image, like a boy playing with a ball. Now, this is an image captioning task. Now, typically, there is another task also called visual question answering. Let's say you had an image of some content inside this, let's call it I. Then you had a corresponding question to this image. This will usually be in the form of text. Now, we send this both in image and the text as an input to our model. Again, this model can be CNN plus RNN, and then we want the output from the model to be nothing but the answer to the question which was asked. So this is another application of these combining CNNs with RNNs. Uh, so even there are further more applications and video aspects when you go, like video classification, action recognition, etc. that you can explore in your own time. But these are the more fundamental or basic type of tasks that you can do when you want CNN and RNN modules. While typically these were initially started off like image captioning and BQA tasks, these were previously you use these hybrid CNN and RNNs. In today's world, most of these are being replaced with multimodal LLMs. So if you people are familiar with models like Lava or Phi, even Phi 4 came out. And then there is like Quen vision model, etc. So these models basically they also in some form do the same thing like what CNN and RNN does. What does CNN do? It will try to process the images. What does RNN do? It will try to understand the question, and then it will try to answer, right? So typically these models which are written in red, Lava, Phi 4, Quen 2, they also have components which will do the same type of tasks. Like there is a component which will understand what is there in the image. Then there is a component which will understand what is the question. And then there is a component which will try to mix these two mix these two inputs and try to answer the question. But the architecture which is used is not CN and RNNs. It is complete transformers. So, and that is why transformers are very helpful and important because you can use just transformers and you can technically replace both CNNs and RNNs with just using transformers altogether. Even for processing images, you can use transformers. Even for processing text, you can use transformers. The only downside is you'll need a there are a lot many parameters like very huge models, and also computationally it is slightly expensive. Okay. Any doubts? As usual, if you have any doubts, you can unmute and ask, or you can also post your queries in the chat. And as usual, like every other week, we will follow the same pattern. First half, we will discuss few questions. Second half, we will do a code walkthrough. In today's session, we will do implement a complete transformer from scratch using just PyTorch. Okay. So coming to the first question, very simple question. It says, given an input dataset X, can the encoder of a denoising autoencoder learn a many to one mapping from X to X? So it's a simple yes or no question. So many to one is basically any input can it map to one particular type of an output. That is what many to one mapping is. An autoencoder, what does it do? It tries to recreate the input itself, right? Like if you give X as an input to autoencoder, the output will also be reconstruction of that X itself. But the question is asking only about the encoder part of it. So be careful. So let me pause for a few seconds. Try to post your answers in your chat. I think there are some answers already. Yes, the correct answer is it can do many to one mapping. So a most simplest example we think about denoising autoencoder, right? So technically, what does denoising do? So if let's say I have this original image X, okay, then how does noise happen? You had some Gaussian noise, okay. Let's so they can they're typically Gaussian as a probability, right? You can add different ways of Gaussian noise to an image. So what does this lead to? So if you start adding noise, so you will get X1 by some if you take some probability of Gaussian noise. I'm just writing over here. Another sample of Gaussian noise if you do, you get X2. And another sample of Gaussian noise you do, you get X3. But ideally, the original X is what the autoencoder tries to recreate. So all of these X1, X2, X3, if any of these you send it to the model, which is nothing but the autoencoder, this will try to output your original X itself. So as you can see, there is many options like X1, X2, X3. All of them are getting mapped to only one option, which is the original X. So yes, technically we can have such many to one mapping here. While the question is only encoder, also even if you use the entire architecture only encoder, it doesn't matter. It will still work because the encoder is the part of the entire architecture. It's not separate, right? So it will still do the same thing of many to one mapping. So I hope this is clear. Any doubts in this particular question? Okay, great. Then let's move to the second problem. So it's a multi-correct answer question over here. So it is based on the context vector attention mechanism. This is not transformers. This is the just before transformers, only using context vector attention mechanism. So there are four statements. Read each of these statements and answer which are most likely to be true. So I'll quickly pause for a few seconds. Try to read each statement properly and answer the question. Just try to take any guesses. What do you think could be the correct answers? If you take a guess, then you know where your understanding is going wrong also. Okay. So let me discuss. The correct answers are likely to be true statements is option 2 and option 4, B and D. Sorry, B and D. So let's first discuss like what is this context vector based attention mechanism itself. So this was explained in much more detail in the recorded lectures. I'll just give you an overview. If there are any doubts, we can discuss it towards the end of the session again. So here, let's say we are having hidden states which are from RNNs, right, which we saw H1 to let's say HD. And this is the encoder hidden states, and there will be something called as a context context vector CT, and then decoder will also have the different output which we call S1 to ST. Let's call it S1 to ST. So now what is this context helping us is when you're processing the output ST, right, which is the decoder's ST, which will generate the final output. This context will look at every other uh, hidden state which is present in the encoder, not just the T till whatever the final value which is there, whatever final value which is there, H capital T. This particular context will look at every particular hidden state in the encoder, and then it will assign some weights to them, which we call attention weights, alpha 1, alpha 2, and so on, some alpha T. Now, because of these, what are these attention weights? You can simply think of these weights as priority, weightage, simple. So, what does it mean? So, ST output, which is there, to get this output, what are the different inputs, like how much is different input hidden states are dependent to get this output ST? That is what this meaning is, context vector. What it's trying to do is identify what is the different influence of different hidden states in the encoder in generating a particular time steps output. That is what at the end of the day context vector attention mechanism is trying to achieve. And then there is formulas for it, how you can do it. You multiply ct is nothing but alpha t into the alpha t into the hidden states, and alpha is again calculated using a bunch of different formulas. So this is where your transformers comes into picture. This alpha t based, so alpha t has different forms to calculate. Typically you have softmax based values, or you can also calculate using some general alpha product values and etc. So here, based on the different formulations, you have different types of attention mechanism. One such attention mechanism is self attention mechanism, and your entire transformers is based on the self attention mechanism. We will see clearly how that happens, but I hope you get the idea that pre-transformers, attention was used in this manner. You had something called as a context vector, CT. This used to identify what is the influence of the different hidden states in the encoder. Let me write it here. The bottom ones are the encoder. The top ones are the decoder, which will basically generate the output. Now, CT is basically trying to identify the influence of different encoders, encoder hidden states on generating a particular time steps output. Okay, and how does it identify the influence? With the help of something called as the attention weights called alpha. Now, uh, so it's also called alignment weights, attention weights, alignment weights. It means the same thing. Now, based on this understanding, let's look at the options. The first one says alignment weights can be negative, but their expected value over the distribution of the hidden states is always positive. This is not true because typically alignment weights are the output from a softmax value, which is always positive. So alignment weights, it's not typically negative. It's mostly always positive. Second says, so first statement is false. The second option says if the context vector CT does not consider connections from hidden state HK, where K is greater than capital T, it may not work as well with those connections. So what it is trying to say is, let's say for some reason, when you are calculating CT, it is only looking at till this point in the hidden states of the encode. All the hidden states after this yellow color line, it's not being considered. And then question is, if it's not being considered, will this particular network or architecture still work properly or not? So the answer is no, because we ideally want the output to depend on all the input hidden states. If you're missing out on a chunk, then it doesn't make sense for the output to be generated without even looking at the entire sentence. It's like, imagine you're reading a book. You didn't completely read the book. You read like 50% of the book. Someone asks you a question. Based on your 50% knowledge, you're answering. But maybe the actual answer to the question lies in the other 50% which you didn't read. So very typical, like take the same analogy and apply it here. So it's saying that if you stop at this yellow color hidden state and you don't look at the future hidden states of the encoder, then you'll never really get it done, right? Then so you'll never really properly give the output. It won't solve the task. It will only give some 50 or some vague answers or incorrect answers. So that is what option two is true. It says that it won't work well, so it is true. Option D is the opposite of option 2. It says even if you don't consider it, it may work well, which is not true, which I just explained. It is not correct. Finally, fourth one says such a mechanism can be made to work for spatio-temporal data, such as videos. That is true. That's what I said, that sequence-to-sequence model can easily be applied to videos, because videos is nothing but bunch of images, image to image, sequence to sequence data type of a thing, and you can apply all these context based algorithms and everything for that particular videos, which is nothing but images as input sequence. So the correct answer is B and D, 2 and 4. Any doubts, anything that is unclear about the architecture, any of the options which we discussed? Yeah, so T is typically all the time steps. So think of time steps while in our typical day-to-day life we think about the wall clock time steps, right? In these usual problems, time steps can be based on the number of like the number of words in an input sentence, that is also considered time steps, right? Because each word is like one particular hidden state that is being generated. So time steps is nothing but the number of units of number of sequence units in your input sequence. Think of it that. So yeah, if your question is like we need to look at all the hidden time steps, encoder hidden time steps for calculating context, yes. Yes, ideally we want to consider the entire page, which is problematic when the content is huge. That's a long-term dependency problem, long context problem, which I was talking about, where RNNs and typically these algorithms fail, and that's where transformers help us do it better. Okay, then let's go to the next question. Again, here we are asking for what are the false statements, and multi correct answers are possible. Just read each of the options clearly and try to guess. Doesn't matter if it's wrong, please try to guess whatever you think is potentially right. Then you'll understand what is the thinking process and what should be answered correctly. Okay, let's discuss the answers. True, four is wrong, but others are also wrong. Like only one is a true statement. Two, three, four, all of them are false statements. So here there's nothing to much discuss upon an architecture per se. I think we can read the statements and then I'll explain it. So first one, I think everyone understands how attention, in this case, the context attention, which you just saw, right? How that can help in image caption techniques. So basically, if you're looking at an image and if you're trying to figure out, you're generating an output which is a text, right? And then each particular word will kind of tell you what particular patch in an image is being looked at to generate that word. So with this, it is kind of, we are kind of getting a peek inside how the model is actually learning. Because let's say if the model outputs grass, but uh, in the image it is highlighting a patch of sky, but it is saying as grass, then we can quickly see, okay, there's a learning mismatch that is happening. We should give more examples or whatever you want to improve it. But at least you get an idea of how, using these attention mechanisms, you can understand the output words and how are they dependent on what input image patches. So in this way, the attention mechanism will definitely help explain failure cases better compared to all the other previous techniques that were being used. Second is, the decoder of a visual dialogue system cannot be truly discriminative as it involves computing the maximum log likelihood of the correct option. So, what is a visual dialogue system? A visual dialogue system is, you give an input image. It's like Chat GPT kind of a thing. So you upload a particular document, or you upload the document doesn't have to be text itself. It can be images also. You can upload a particular PDF of a image or whatever it was to the Chat GPT, and based on that, your entire chat you can have like one-to-one conversation, like multi-turn conversation, right? You can ask question one to ChatGPT, it will give you an answer output. Then you ask something, another question related to the same document. You don't have to upload it again. You upload it only once. So this back and forth conversation, which is called multi-turn conversation, that if it's involving images also, it is called visual dialogue system. So the question is, can it be truly discriminative? It can be truly discriminative because the visual dialogue, the decoder of this typical visual dialogue system, so not the ChatGPT one, but this particular visual dialogue systems, which is discussed in their lectures, they actually try to answer finally in like if you want to more deterministic, like okay, one option has higher probability compared to all the other options which are possible. So yes, they can be deterministic too. So this second option is wrong. Third is about a metric called blue score. So unless you've gone through the lectures, you would not. It's not very intuitive what is a blue score. So blue score is nothing but, you can think about it in a very simple terms. It's a matching metric between the generated text by the model and the actual ground truth text. How do you match? You can either match one word at a time, two words at a time, three words at a time, or n words at a time. So blue score is basically looking at word to word level matching at different instances, one word, two word, three word, and will try to come up with a score on whether it is good or bad. And typically the range of blue score is between 0 to 1, not 1 to E. Then comes transformers. So I've been talking about till now transformers are helpful because they process the data in parallel manner, unlike sequential manner. While that is true, the statement over here is slightly misleading because it says transformers are parallelizable architectures in the sense that multiple models with the same architecture and weights can be run parallelly on multiple devices, whereas RNNs cannot. This is wrong. Transformers are parallel because the different words which are being sent as an input to the model, all of them can be processed together at once. That is the parallelization of transformers. This sentence which is giving, this is generic for any parallelization of deep learning models. It has nothing to do with transformers. So maybe let me show it, show what I'm saying. So let's say I have three words. I am a tree. Okay. Now typical RNNs, it will look at I, then it will look at am, then it will look at then it look at tree. This is how you have that hidden stage going one after the other. Now if you're taking a transformer, it will take all the send words at once and then it will process at once. How does it process? It will calculate the attention, which you will see in the later slides. But that is how it does. So instead of looking at one after the other, it'll take all the words at once and calculate, okay, what is the relations between all the words that are given as an input. So statement 4 is false. The definition of parallelization is not is had nothing to do with transformer architecture. It's a general definition. Any doubts? Any option that is unclear, and or you want me to repeat something? Okay. Then let's go ahead. Again, this is a multi correct answer, and we have to find the true statements. This is related to the transformers and vision transformer architectures. So I'll pause for a few seconds, and then you can read each option clearly and let me know the correct answer. Okay, let's discuss all of the options properly. So correct option is the three option, which has already been answered. But let's discuss each of the options and why it is, what are the correct and wrong answers. So the first one says vision transformers do not require positional encoding as they are not temporal data, which is not true. So typically, let's discuss transformers on a high level. When we do the coding, I'll go in detail. So how does a typical transformer architecture looks like? You have your input. When I'm writing I, it doesn't mean images per se. Could be any input. Mm. Then you have a block for positional encoding, which we call PE. Then we have our encoder. Then there is a decoder, and then the decoder will basically generate the output. And the data flow is standard. Like input goes to positional encoding goes to encoder. From encoder, you send it to decoder, and decoder will send it to output. Now, this input, what we typically, if you have a sentence that is already considered as each sentence is broken down into words or tokens. Tokens are not actually words. There are some tokens doesn't even actually consider as one whole word also. But for simplicity, you can consider each word to be a token. So typically, if it's text data, your input will be a bunch of tokens or words, and each of, since it's a text data, let's say the same example, I am a tree. So you have some ordering, right? Like I is at the first position, am is at the second position, is at the third position, tree is at the fourth position. There is some ordering. So this positional embedding basically captures that ordering of I am a tree, like that particular ordering. It will be captured by positional embedding. Now for images, I'm gonna draw it on the bottom. Now for images, there is no position, right? Like this is it. This is your entire image. It has, okay, there are some objects in the image that doesn't matter. But still, what will you say? What is the position of this particular different aspects in the image? So that is where people mm, mm, created something smart. What they did was, let's break this image into patches. Okay, they called this each as patches basically, and then they call this patch one, patch two, patch three, patch four. And now we know fundamentally, spatially looking at it, patch one comes before patch two, and then patch three comes, and then patch four comes. So if you unroll this, you'll have something like this: patch one, patch two, patch three, patch four. Okay. And there are different ways to do this. This is called the patchifying or patchification algorithm. There are advanced ways to do this, and what I'm explaining is the most uh, generic or the high level overview. Okay, you get these different patches, and now once you have these patches, there is an ordering, and again, positional encoding will look at this. Will send this ordering will be captured by positional encoding. Patch one, patch two, patch three, patch four. That ordering is now being captured by positional encoding. So this is typically the difference between vision transformers and normal transformers. In vision transformers, there's a pre-processing step where you have to patchify your input data. That is converting a single image into different patches. Once you do that, you treat each patch as your standard word token, which you do when you have text data, and then you repeat the entire transformer architecture as it is. So that is the only difference. That is a major difference between vision transformers and generic transformers. So that being discussed, what is the first option? First option says vision transformers do not require positional encoding. False, because while it is not temporal data, we still create a pseudo sequential type of a data by creating patches, and we still need encoding. So first option is false. Second says input data is parallelly passed to all the stacked encoders in a transformer, which is again wrong. If you see the green arrows on the top, the input is sent to the encoder, and inside actually encoder there are multiple blocks, like layers are there inside. So the data is going one after the other. So after positional encoding, it will go to the first encoder layer. From there, it will go to the second encoding layer. From there, it will go to the third encoding layer, and so on. So it is not like that each the input is going to each layer separately. It is one after the other. One layer's output is the next layer's input. Typically, like your CNN architecture also. So the second option is also false. Third option says input data is parallelly passed to all stacked decoders from the last stacked encoder. That is true. So that is where the encoder output is sent to all the decoder layers parallelly. So this particular is the standard architecture of transformers. Why do we do that? We do that because we want to carry forward the understanding which you learn from the encoders to every decoder layer. That is the idea of this passing all the information from the stacked encoder, last stacked encoder to all the decoders. Then it says fourth option, the weight values in each QKV matrix of multiple heads of the first encoder of a single transformer are kept exactly the same, but the inputs to the matrix are kept varied to ensure better generalization. This is false. Typically, the weights are the ones which you are learning, which is not fixed. Instead, the input, which is like we have the WX, right? At the end of the day, we do W into X. At the end of the day, we do W multiplied with X matrix, W matrix multiplied with X matrix. So it's always the input which is fixed and the W which is changing. So the statement 4 says weight values are constant, which are exactly the same, which is wrong. Weight values are the ones which you're actually learning through the training process. So fourth option is also wrong. The only correct option is option 3. Let me pause for a few seconds. Any doubts? Anything that you want me to discuss again? I know the architecture I didn't go in depth because I kept that for the code walkthrough, but this block level is enough for you to answer these 4 questions. If you want, we'll clearly discuss what are these QKV when we do the code walkthrough. But if is the block level diagram clear? Okay. Let me go to this next question then. So this is the in this question you're given the equation for the standard self attention, which is the softmax multi of QK transpose divided by square root of DK multiplied by the value vector. And you're given that Q and K are dimensions of DQ cross DK. And you are saying now the question is, let's assume that Q is all the entries in Q is multiplied by a scalar X. All the element entries in K is multiplied with scalar Y. And now, since you updated by multiplying this x and y, the question is there are 5 different values for this x and y pairs, and which one will increase the softmax distribution towards the uniform distribution. So, what is saying accordingly denote up arrow to all the events where the modified softmax probabilities will be closer to the uniform distribution. Use down arrow if the event will move farther away from uniform distribution, or just use this slash or just straight vertical line if they do not change. So think about it, and maybe you can just answer for the first question, or try to come up with the logic on how we can do. We don't have to solve all. Maybe just try to solve the first question. And but what should be the logic behind identifying whether this modified QK values which are being multiplied, will it make the softmax distribution closer to uniform or farther away from uniform, or no change? So please try to read the question once again. I'll pause for a minute. Okay, let me discuss what logic you have to use over here. So, what is the formula? Sorry, the formula is highlighted over here, and we are saying ki instead of the typical qk, we multiply each q with x, each k with y. Since it's a matrix multiplication, since all the elements are multiplied with x and y, they'll come out. So, what will be the new softmax? New attention, I'm writing on the top. New attention will be nothing but x into y times the old attention. Nothing else changes. So it's not. Sorry, let me. So new attention will not be directly like this. New attention will be softmax of x into y into the old values, the q, k transpose divided by square root of d in, yeah, and this will be into v as it is. So this will be the new attention. The only thing is you're now multiplying this x into y. So everyone might be aware of temperature scaling in softmax. If not, let's discuss that first, because this is nothing but temperature scaling of softmax. So what does typically a softmax do? What is softmax? Given an input vector, let's call it x bar. The values can be any values. It could be anything between minus infinity to infinity. If you send it to softmax, it will basically create a distribution. Okay, it doesn't have to be uniform normal distribution. It could be any distribution. It creates a distribution. What does it mean? That if you sum all the elements, if you sum all these elements, it should be equal to 1. So it's a distribution, right? It's a typical distribution. That's what softmax is doing, converting any vector into a distribution where if you sum up all the values, it will be 1. So what does it mean? Each of the values will be something like this will be 0 0.1, 0 0.1. Let's say this will be 0.8. So this is how you're now converting the unbounded value from minus infinity to infinity. You're now making all of the values to be in the range of 0 to 1. And now coming back to the question, we are saying, okay, we are multiplying with some constant, and that constant is nothing but x into y. So if your original distribution was 0 0.1, 0 0.1, 0 0.8, now let's say we multiplied with some x and y whose value is greater than 1. So let's uh, maybe let me take it in this way. It'll be clear. Let's take just two numbers for simplicity. Let's say my input to the softmax is just these values, original values, 1, comma 2. Okay. Now I have two options for x into y. X into y, it could be either something like 0.5 or could be 1, or it could be, let's say, now x into y if it's 0.5. So we multiply each of these values 0.5 with each of these x bar, right? Elements of x bar. So x bar, what will it be? It will be 0.5, comma 1. Similarly, if you multiply 1, it will be the same as it is, no difference. And now it will be 2, comma 4. So I hope you're seeing the difference. When you're multiplying with something x into y less than 1, the distance between the two things came closer. Previously, the distance between the two elements in x bar was 1 unit. Now the distance in the first case, this leftmost case, the distance between the two elements is just 0.5. Whereas in the rightmost case, when xy is greater than 1, the distance increases. It becomes 2 times. Whereas originally it was just once, 1 unit away. And if it's just xy is 1, there is no difference. So this is the condition you need to know. The condition what we are trying to come over here is, if xy is greater than 1, then you will create a distribution which is farther away from uniform. If xy is equals to 1, then there is no change. If xy is less than 1, then it is coming closer to uniform distribution. So once you have you can solve all the questions the same. With each of them are xy, just multiply and check whether it is greater than 1, less than 1, or equal to 1. and based on that you can tell what type of a distribution will be formed. Is this clear, or any doubts, or do you want me to repeat this again? Okay, great. Then let's go to problems. Last problem. It's based on the positional encoding of the transformers. I told you there's a positional encoding, right? Typically positional encoding, I'll show you the formula also for this. So P of I comma J is how positional encoding is represented, where I is the entry in the ith row and J is the column of the position encoding matrix, jth column of the position encoding matrix. We are asking, the question is, under which of the following conditions does P of I comma 2J equals to P of M comma 2N? The standard formula for position embedding is as follows. P at even positions, let me this way, even positions is equal to sine of a certain value x, let's call it. P at odd positions is equals to cos of certain value x. Okay, now we are basically saying that uh, we want to P of I comma 2j and P of M comma 2n. So both of them are even, 2j 2n, right? So we are only considering the sine values. So we are saying we have two sine values. Sine of, let's call it xj, must be equal to sine of xn. Okay. How does two sine values be equal? There are two conditions. Let me show the answer itself. So sin x and sin y, how are they equal? There are two conditions. Either you take the modulus of y minus x should be equal to sum 2k divided by pi, or it could be y is equals to x. But we are, in our particular question, we want all the positional embeddings to typically be rational numbers over here. So that is why we say we are only concerned the second condition of y is equals to x. And if you know y is equal to x, then just apply the values. So now P of I comma 2j is nothing but sine of that x value, sine of the other one is y value. So you just have to equate them. I divided by 10,000 to the power 2j by d model is equals to m divided by 10,000 to the power 2n by d model. So you just multiply, cross multiply, and just simplify, and you will get the answers A and B to be this particular conditions when these particular position embedding encoding mechanisms will be equal to each other. I know I didn't give you time to solve it because this involves understanding this formula and all. I just want you to know that these are also ways in which you can solve the problems. So you can take your time, maybe once you after this session, and read this question once again properly, and then you can get back to me if you didn't understand. But the idea is you have to realize that when you're saying two position embeddings and both of them are even, right? So all you're concerned about is sign values. Once you know what is the formula, you just have to use trigonometric relations that sin x equals to sin y only when these two conditions are possible. Y minus x is equals to 2k by pi, or y is equals to x. And since we only want rational numbers, we don't want the first option, we want the second option, which is y is equals to x. And the how once you equate this y is equal to x, you'll get an equation, or and this equation, if you simplify, you will see two options being the same. Okay. Any doubt in this last question? Anything like or any doubt in any other questions we discussed till now? Okay. Then let's move ahead and go to the code walkthrough. So, like I mentioned, in today's code walkthrough, we will discuss about the attention mechanism and also build the entire transformer architecture from scratch. So, this is some library torch text. Don't have to worry. It's like a small library to deal with textual type of data. But this is the main architecture itself. So, I've already discussed the block level overview, but let's go ahead and see. So, this is typically the encoder block. Okay. And encoder block, how, what are the different components? The first is, let's say this is the input, hello input, and then there is tokenization and embedding. What is tokenization and embedding? The first thing is tokenization. Like I said, given your input sentence, you need to come up with smaller units of that input. It could be each word, that is called as a token. But typically, like I said, tokens are not actually each word. There are like subwords and other aspects of things are also there in NLP. But for our simplification, you call it each word as token. So we take that input sentence and we break it into tokens. That is the tokenization. But even after doing tokenization, let's say here, hello will become one token, I will become one token, love will become one token, you will become another token. Now, each of these tokens is still a word in English language, which humans understand. But for machines, it doesn't make sense to give an English word. We need to represent that using a good vector. That is where embedding comes into picture. Embedding basically converts each of these words in English language into a vector. Now, what is these vectors? Where are these coming from? So typically, there are like these standard embedding vectors available, which have learned, which have been trained in such a way that there are some semantic relationship between each of these vectors. Like for example, hello, how are you? Let's say there are four vectors. Hello is one vector, how is one vector, are is another vector, uh, how are you? You is another vector. So we know that there is the likelihood of hello, how are you coming together is very high, because that is a very common way people greet each other. Now, when you're learning this particular embedding matrix or vectors, you learn these most commonly occurring patterns and correlations of all these tokens vectors with each other. So ideally, we want all of these four vectors to be close by in this in an embedding space. So if someone says ki, okay, hello, how are you? These are the four vectors for hello, how are you? And if you find the dot product, which is nothing but a similarity, right? The cosine similarity. If you find the dot product of these four, they will be relatively much closer compared to other random words like America, which is not very commonly occurring with hello, how are you? So I hope you understand what I'm trying to convey over here. What are these embedding vectors? These embedding vectors try to uh, is a representation that we convert each of these tokens to machine algorithm understandable vectors. And the embedding vector should not be random. They should be in such a way that just what are the most commonly occurring tokens in each other with each other in the world, right? Those corresponding vectors should also be very close in nature in the embedding space. Let me pause at that point. Is that particular concept clear? Because it's very important to understand each and every block, otherwise, it'll be hard for you to understand the overall picture. Do you want me to repeat this embedding matrix or vectors? How are they created? What is the idea behind it? So, if that is clear, let's go ahead. So, first you do tokenization and embedding. And so, great question. It's not just frequency. So there is an entire research what do you say, field in itself on how to create these embedding vectors. So it's not typically just frequency. It's also about semantic meaning. Also, not like maybe sometimes like and the they occur very high in nature with each other, but semantically they might not make a lot of sense. Semantically, some other words in between and the might make more sense. So these are again, these are not like fixed rules which we give. We basically take a bunch of huge corpus of data, like a lot of Wikipedia articles and everything, and you send that as an input to these embedding matrices to learn these embedding matrices. You give that entire pool of data, and you expect that these semantic meanings, along with frequency and other aspects, all of them are learned together. So we can maybe I can get some literature on how this is done of embedding matrix that we can see here today. Also, we'll see, but typically for standard LLMs, right, we use pre-trained embedding matrices. That is a better way to do it. They learn from a lot of huge corpus of internet data. Okay. Is that clear? I hope that answered the question. Then next, yeah. Then the next is the positional encoding. Uh, Here the positional encoding, like I just said, right? So each of these positional encoding tries to capture that notion of order that is present in your input data. Hello is the first order, second I love, and then you. These are all different order. So why do we need this again? All of these, the problem, not problem, the way transformers are processing data is all tokens together. RNNs did one after the other. So implicitly in RNNs, there was ordering without even us explicitly saying, right? There was ordering because it processed one after the other. But here, since you're giving all of them together, they should make some sense for the model to understand what is the right way to write a sentence, right? Otherwise, it will just randomly gibberishly give, I think there was a question, right? Frequency. Let's say hello, I love you, there was no order, it will always give I you together because they frequently occur without even making sense to that entire sentence. So ordering is very important. And how do we do this positional encoding? Like we just saw, even ones will have sinusoidal encoding, odd positions will have cosine encodings. Then we send it to the encoder block. So here in the encoder block we have three different concepts over here. First is the multi-head attention. We will see in detail next. Next is the layer normalization. It is like a typical batch normalization of sorts, but instead of normalizing across batches, it will do across layer. Then you have the concatenate, add whatever you know, it's the residual connections which we have. Um, and then you have the typical MLP layer. And this MLP layer, again, the need over here is for learning better representations. I will explain how it is, where it is, when we pass through the linear layer. So this is a one encoder block. You repeat this n number of times. That's why you say n times this block, right? N number of times we repeat, and then finally you create certain uh, vectors. What are these vectors? Query, keys, and values. So I think it's a good time to understand what are these with these examples. Just give me 1 minute. Sorry. Sorry for that. So let's understand these particular with the working of this encoder decoder with the help of the example. So here you are doing machine translation. Input is a French word, French sentence, and the output should be in English language. I am a student. So here we send each of these three words all together to the encoders. An encoder, like I said, there are n number of encoder blocks. Each block consists of these three different sub blocks. Like that, there are n number of encoder blocks. All of them, output of that last encoder block is sent to the decoder, and the decoder when will output I am a student. What is happening inside? Let's open and see. Okay, input. Let's say here what is there? 1, 2, 3, 4, 5, 6. 6 encoder layers. All the three words will go to the first encoder, and inside that first encoder there is multi-head attention, there is normalization, there is residual connections, then there is linear layers, and that output is sent to the second encoder layer. Again, you repeat the process, send it to the third encoder, and finally, the last encoder output is now sent to each of the decoder. Why? So we saw this before also. Why do we do this? We do this because we want the semantic meaning of what was being encoded to carry forward to all the layers in the decoder. Otherwise, it's usually hard the meaning to get lost if you don't carry forward to each decoder. Inside decoder also we have very similar attention block. Instead of a simple attention block, we have encoder decoder attention. Because why? Because here we are looking at the The input is coming from the encoder side, right? So that's why we call it encoder decoder attention. But you have the same attention mechanism, normalization, residual connection, linear layers, and then the output for each decoder layer. And finally, your last decoder layer will give the output as I am a student. Now let's look at in more clear terms. We just saw this, but again, input embedding, positional encoding, multi-layer attention, normalization, feed forward. This will go into this. So in decoder, this is the different attentions. One is masked multi-layer attention. This is the output itself. So because output will be done in a word after word manner, right? We call it auto-regressive basically. So what do we mean by that? When it is generating, it won't generate I am a student at one time. It will first generate I. Now this I will go as an input back to the decoder, and then it will generate am. Now this I am will, both of them will go as an input back to the decoder, and it will come. Now each time you're generating one word from the model, okay, and that is why we call it auto regressive. So like each time only one particular word, and that word will be sent as an input along with the encoder hidden states as an input to the decoder. So that is why here we have two different attention. The first is the masked multi-layer attention, which will take the input from the uh, previous tokens that got predicted. Or if it's the starting, we will send a special tag called start special tag, which will go as an input. And this line which is coming from encoder, this is that special attention block, which is an encoder decoder attention. Right? That is because now you're calculating the attention between the encoder hidden states and the output decoder outputs. And then finally, you send to a linear layer, which will call to the softmax, and you generate the next token. Then you repeat this process until you generate all your tokens, output tokens, whichever you want to generate. Okay. This is the overall idea. Before me diving deeper into the actual vectors calculation and everything, vector multiplication and all, is this clear till now? Any doubts, anything that you want me to repeat? That's great. Mm. So, as usual, we want to first import libraries, which is always a very good standard practice for coding. Import all your necessary libraries at one place. And here we're using just PyTorch. And we have these helper libraries like Pandas, NumPy, Seaborn, and Matplotlib, which will basically help in different mini operations like Matplotlib to visualize stuff, Pandas to handle CSV type of data, NumPy to do some other operations, arithmetic operations, and etc. Okay. Now the first thing is creating word embeddings. So typically we first fix an embedding vector size. Now, how do we fix it? It's like you try out with different again dimensions of that particular vector you want. So typically we have 512 to be the embedding vector dimension, but you can use any of it, any vector dimension size. In this case, it's 512. And let's say we have the vocab size of 100. So what does this vocab size mean? Vocab size means all the unique possible words for this particular task. So ideally, if you think about it for English language, the vocab size would be the number of words in the dictionary. So think of it like that. Now, if I'm trying to solve a given task, there should be a dictionary reference for the model, right? Now, that dictionary number of unique words in that dictionary is the vocab size. So in this case, you're saying, okay, the vocab size or the dictionary size is 100. So there are only 100 unique possible tokens. And out of these 100 tokens, you generate whatever output you can. And each token will have a vector, will can be embedded as a vector of size 512 dimensions. Okay, so total embedding matrix, what it will be? It will be 100 cross 512 size. Now, if you have again a batch size of 32 and sequence length of 10 words, the total output will be 32 cross 10 cross 512. So what is happening? 32 is the batch size. Each batch size, inside that batch, each one will be an input sequence, and each of them input sequence is, let's say, 10 words, and each word will have 512 dimension vector, right? So that is why we have 32 cross 10 cross 512. The matrix is different. 100 cross 512 is a lookup table. Now, let's say if you have 32 cross 32 cross 10 as your input. Now, for each input word, this 10 input word, you need a vector, right? How do you get that? You look at this table, 100 cross 512 matrix table, and then you get the output as 10 cross 5. So I hope this is clear. So try to stop, uh, try to ask any questions in between. I'll just keep on moving forward till then. Okay. How do we do this in terms of code? This is how it is. We just create a class embedding. Again, these are all neural network classes what we're creating till now. So always make sure in any neural network class, just like I told previously also, always inherit the nn dot module. If you don't do this inherit the nn dot module, it won't tell the PyTorch that this is a neural network class, and then it won't do the training which you want it to do. And every neural network class has two important functions: init function, forward function. There are other functions also, but unless you want to modify backward pass and everything, you can use the default other functions. All you have to usually worry about is init function, where you define the global variables. Like here we are defining what should be the embedding matrix itself, the size. You're saying the vocab size, embed size, you define that. Next is the forward function, where you define the data itself, how it should flow. So what is happening? You're getting the input X, you're sending that to the embedding matrix, that lookup table, and the output will be this 32 cross 10 cross 512. The output, what do you say, embedding in, it's basically the tokenization and embedding, right? That is what this out represents. Okay. Next is positional encoding. Like I said, the motivation or the intuition behind positional encoding is to understand the order of the different tokens in the input sequence. How do we do it? This is the two equations for all the even position, even time steps or even positions. We have sinusoidal function. For all the odd positions, we have cosine function. Now the question is this the only way to do positional encoding? No, this was the one which was used in the original paper. Attention is all you need paper. But over a, this was published, I think, in 2017 or 18. I'm not sure. But of course, in the last almost 6 7 years, there have been several improvements, variants to the same sine and cos, and different ways to do it. We can always look into it, but all of them, the idea remains the same, and the place at which you place these encoders will also remain the same. It's just the equations which will change. Each of them will have different way of capturing that ordering based on the different equations. In this case, in this particular example, we will follow the official paper, use the same sine and cos. So there are two arguments you have to worry about. First is the position, where it refers to the order in the sequence in the sentence. Okay. Second is the I, which refers to the position in the embedding vector which you created, right? Because embed here, what you're getting out from out, you're getting 32 cross 10 cross 512. Okay, so the POS argument will correspond to the 10 dimension in the 32 cross 10 cross 500, the second dimension, the 10 elements in that. I refers to that 512 dimension out of 512, which is the position of I. Out of the 10 different second dimension, the POS will tell which particular position to look. Okay. So typically you do an addition between the embedding vector, which is your 32 cross 10 cross 512, and then you add it with the positional encoding matrix, which is also of the same size, 32 cross 10 cross 12. That's how you can add these two things. And then once you add it, you're inherently now converting your original input to a much more um, order aware input. You can, it's not an actual term, but you can think of it in that way. It's much more encoded with positional information type of a thing. Okay. So this is how you do it. Again, this is a neural network class, positional embedding, because we're inheriting an n dot module. In an init function, we define the embedding dimension, which is 512. Then we write that equation itself, that entire sine and cos for each position and each uh, element in that embedding vector. That's why we have two for loops. Now, once you do that, in the forward function, whenever you get the input x, which is that previous embedding output, right? You'll take that x, you first multiply with the square root of the embedding dimension, then you add it with the positional sequence values itself, and that is what you do. It's nothing but these two matrices adding with each other. Okay. Now let's go into self-attention mechanism itself. So typically the self-attention mechanism has three vectors. Let's now go back to the original image. So there are three important vectors in self-attention: query, key, and value. Now, what are these query, key, and value? Query and key is like if you take hello, I love you. These are the three different tokens. Now, if I want to understand what is the relationship between each of these words with amongst each other, like if I'm talking about hello, what is the other three words importance or influence when I'm looking at hello? Similarly, if I'm looking at I, what are the influence or importance of the other words when I'm focusing on I? Now, how do you do that? You can do that when you take this vector you take two copies of the same vector and you multiply with each other to identify what is the influence of one word on the other words. So that is what query and key does. Key is nothing but another way representation of this same input sequence. Query is another representation of the same input sequence. So query is like, okay, now I'm looking at hello. What are the different keys that you have? I love you. What is the when you multiply query with key, you will identify what is the influence of each of these other three words with hello. That's why you multiply query and key similarity. And of course, then you do weighted mean with attention. And then finally, whatever weights you get, that is the importance for other words, you multiply the actual values of these words with those weights. So this is a very simple way of self-attention mechanism. You have three important vectors: query, key, and value. Query and key are like the same sentence, different copies of it. You try to identify the similarity of each word with itself and the other words. You then do a weighted average or weighted mean of this importance and multiply the actual value of each word with the uh, weighted attention value itself. And that is your output. Now you do this multiple times. That is why it's called multi-head attention. And not just at one encoder block you do multiple times, you do this n number of encoder blocks also. Why do we do this so many different times? Because each of the times when you do the similarity and right, you're capturing different similarity between each of the input sequences, especially if you have like a huge PDF, right, like 50 pages document or something to read. You can quickly see how much random correlations can happen. So you want to eliminate all of them and only learn those particular relations which are most meaningful or most important. So that is why you keep on doing this n number of times. This is where the complexity also increases because you do this n square times kind of a thing. Okay. Any doubts or anything unclear in this intuition of what are these query key values? Because if you understand these idea, then it's nothing but simple vector matrix multiplications that we will see in the next code aspects. But is the idea clear of what is this query key value doing? Okay. If there are no questions, then let me go ahead. Is someone unmuted? If there are questions, please ask. If not, please mute yourselves.
Actually,
Yeah.
in the lecture week 8, there is a example thinking machines.
Uh-huh.
So they have given query keys and values, and they have removed the score of thinking as Q1 into K1 is equal to 112. So how that 112 value they got, I did not understand.
Okay, I don't have that particular example right now. Okay, maybe let's look at it after at the end of the session then,
Okay, sir.
because that particular example I don't have it with me right now. We can look at it uh, after the end at the end of the session.
Okay.
Yeah. Okay. Now let's come to the calculation of the self attention itself. That nothing but that query key and sorry, query key and value matrices. So first step is we have to create three new vectors from that input vector. Now input, if you remember till now, what did we do? We calculated the embeddings, we calculated the positional encodings. That is where we are. Once you get the positional encodings, now the first thing is create three vectors from these positional encodings: query, key, and value vectors. And each vector is of the dimension 64. So now, where did this 64 come from? So if you think about it, the input which is coming to the model is 512 dimensions, that embedding dimension. And we want 8 attention heads. So 8 divided by 512 is 64. So that is why each vector is of the size 64. So this all code will be shared with you. You can look at it in your own time. Very, it's written in detail how we are calculating each dimensions and everything. So don't worry about it. I'm just trying to explain as clearly as possible, but I might miss out on small details. And you can always look into it and get back to me in the next session if anything is unclear. Okay. Then first you calculate the three vectors, 64 dimension each. Next, you calculate the score. Score is nothing but query times query vector multiplied with the k transpose vector, the q into k transpose. Then you get it's like a dot similarity, like it's like dot product between two vectors. That's how you get the score. Now this score is basic, then divided by the square root of the dimension of the key matrix, and then you take the softmax value. That is step 3. In step 4, you multiply the softmax output with the value matrix itself. And finally, you send this entire thing. You repeat this. You're anyways doing it 8 times. You do it parallelly. You don't do it one after the other for all the 8 heads. You then send all of these to the linear layer. So that is how you calculate the multi-head attention and then send it to the linear layer. So let's see how that attention is actually calculated. Again, this is a neural network. So we define the same. So we inherit the NN dot module. We have the two functions init and forward. Inside init, we define all our main variables like embedding dimension 512, number of heads 8. Then each single head dimension is nothing but 64 for each query, key, and value vector. Query matrix is single head dimension cross single head dimension for all the 8 heads. So it'll query matrix is basically the W matrix with which you multiply the input X to get the query Q itself. Similarly, key matrix is also in similar fashion. Value is also created in similar fashion. It's all linear layers. And then finally, output layer is basically which is the linear layer, which will take the number of heads and single head dimension multiplied with each other and output the embedding dimension itself. So one thing to notice in all the attention is, let me show in this block diagram. So each of these encoder block, the input dimension into this encoder block will be 512. The output will also be 512. All of the encoder input output will have same dimensions, 512, 512. In between, we are squeezing, like we're compressing the dimensions, expanding the dimensions, and all happens. But the final input to the encoder block, output to the encoder block will always be 512, 512. So this is how the matrices WK all, like X is all multiplied with WQ, which we just saw that NN dot linear. This is how you get the Q matrix, K matrix, and V matrix. And then you take that QKV, calculate the QK transpose divided by square root, take the softmax to get the scores or final attention scores, and then you multiply with the value matrix. So this is the equations which I just defined in the code itself. Okay. Now forward is very simple. So once you understood that, we first take the input here, the key, query, and value QKV vectors, and each of the values is of the size like this: batch size, sequence length, number of heads, and single head dimension. So in our case, it will be 32, batch size, sequence length 10 words. How many heads? 8, 64 each dimension. So previously we had 512. 512 we're splitting into 8 cross 64. 8 is the attention heads. 64 is each query key or value vector dimension. So, oh, sorry. So this is the key is created, the query is created, the value is created. Okay. And then once you create that key query value, you create the actual key uh, KQV vectors itself. So here, this is how you're getting the output 32 cross 10 cross. We're multiplying with the matrix and getting the actual KQV matrices. And then we transpose. Why do we transpose? We shift from 38 cross 10. Here we are 38 cross 10 cross 8 cross 64. We go to 38 cross 8 cross 10 cross 64. Why do we do this? Because we want each attention head to do in parallel, because if 8 is inside, then we are basically not doing that actual each attention head to be independent of each other. So we want each attention head to be independent of each other, so we are bringing it to the second dimension. So now it will be like this 10 cross 64 is each word's key value, query value, or value vector, and like that there are 8 different copies of each of these 10 cross 64. That is what we want the meaning to be there, so that's why we transpose the dimensions. Then you calculate K transpose, which is that K adjusted to do that QK matrix. Then you do the torch or multiply. Here we do that Q into K transpose. And mask, I'll ignore for now. I'll tell you what it is when you do decoder. For encoder, mask is usually not needed. Then you calculate, you divide that whatever output of QK transpose with the square root of the dimension, which is 64. Square root of 64, which is 8. Apply the softmax, multiply the scores with the value matrix, and then we again transpose it back to our original dimensions, which is 38. First, from 32 cross 8 cross 10 cross 64, you go to 32 cross 10 cross 8 cross 64, and then finally we go to 32 cross 10 cross 5. Now, sorry. Oh. Now, once you get that, you do the residual connection, which is nothing but self dot out. We take that values, and 32 cross 10 cross 512 is going as 32 cross 10 cross 500. This is it. One multi-layer attention is done. Now, let's see what are the different steps in after the multi-layer attention. You have to do the residual connection and normalization, and then the linear layer, and then another residual and normalization. So if you do these three other, the one in pink block, yellow block, and other pink block, if we complete this, we'll complete one encoder block. And after that, you can just have to repeat it a number of times. Okay, how do we do that? The first, in encoder section, the first input we are sending to embedding layer and position encoding layer. Step 1, that is done. We just saw. Step 2, we just saw how to create the multi-layer attention layer. So that is also completed. Step 3, we need the normalization and residual connection. So here the output of multi-layer attention is 32 cross 10 cross 512. We gets added with 32 cross 12 cross 512 of the input. Residual connection is just addition, right? So it's going from the input to the, so you see this connection from input to the output. This is the residual connection. Okay. And then step 4, we send it to the feed forward layers, where you project it into higher dimension, and then you come back into lower dimensions, and then you learn better features. That is what the idea of linear layers over here is. So what are the dimensions? So you first send from 512 to a higher dimension 204. You do your linear layer MLP multiplications over there, and then you come back to 5. And then finally, again, we have our final residual layer and the normalization. Okay, this is the one transformer block, which let's see how we can do that. This multi-layer attention is just what we created in the previous code block. That is what we're creating as an instance. We have two different layer normalizations. These are again existing in PyTorch. You don't have to write or worry about. And then this is the MLP layer, where we have one linear layer where you expand it, the dimensions from 512 to 2048. You do the non-linear activation over there. Then you come back from the higher dimension 2048 to original dimension 5. And then you have two dropouts. So let's look at the forward function. You get the key query values, which is nothing but the input only 3 times. You send it to the attention, get the attention output. Here the size is 32 cross 10 cross 5. You add it with the original value itself. That is what the residual connection. Then you do normalization, self.norm1. Then you do a dropout for better generalization. Now this is sent to the feed forward network. Now feed forward network output is again we do a residual connection, And then we do a second normalization dropout. This is the output of the encoder block. So once this is clear, you just create your entire encoder, all the encoder layers, by just writing a for loop. You just write for layer and number of layers, self dot layers. You repeat the same layer which you just created. This is the token. Sorry, self dot layers is the module transform block which you just created, right? So we just replicate that for n number of layers. We have number of layers, like I think typically it's 32 or something. I'm not sure, but yeah, you replicate it how many number of times given, and then for each layer you just send the out input to one layer is nothing but the output of the other layer. So that is what this for loop is doing. Okay, again let me pause. Is this clear up till encoder block? I know I went a little bit fast because it's all the details, everything is mentioned very clearly. You can look into the collab notebook, but is the idea clear, or anything that is mm, very unclear, or like something which you don't understand till now at all? Please let me know. Uh, Sorry, what do you mean by NN dot sequential instead of mapping? Can you please explain? So you mean like module NN dot module list? Yeah, you can. Um, you can use sequential also, but in that you don't have to write the for loop. If you're using sequential, it'll take care of it. But it's typically better if you use the module list because you have more control in this case. It's better to use that. But if you're very sure you won't use in between values at all, then I think you can go with sequential also. That's a good question. You can try and check. Ideally, we typically follow the module list. I've never tried it with sequential. You can, I think it should work fine. Okay. If that is clear, let's move to the decoder part. More or less all the components we already have with us. The multi-head attention which we created. It's just that here I didn't explain the mask. I'll explain right now what is the masking. But we already wrote that if condition over there. So that remains the same. The feed forward we just created, that is also there. So entire block is already ready for decoding. And we have to just call that. Before that, let's see what is that masking idea over here. So typically we have these triangular matrix. Why do we have these triangular matrix? Because like I said, the job of a decoder is to generate the output token one after the other. But when you typically send the model as the when you're training, right, the decoder will actually see the entire output sequence also, that is also going as an input itself. But we do want the decoder to actually look at the each token value, so that is why we say 0 at that position. So if you're processing the first decoder output, all the other values which are present in the decoder sequence, input sequence, they all will have 0 value. It means that the decoder won't see what are all the other sequence values that are present as an input to the decoder. So this is the idea of masking, is that you do want the model to leak information. You don't want it to see or peek through the future and see, okay, these are all the next tokens also that will be coming. Training time, we actually pass the entire output sequence as an input to the decoder, but we don't want the model to see all the tokens. That is why we create some mask. That is the basic idea over here. And it's very easy to create this triangular matrix. It's very simple. I'll show you how to create that. Remaining all the other steps remains as it is. So in the decoder block, we again use the same attention, multi-head attention. We create the embedding dimension, number of heads and everything. The same layer norm, dropout, transform block, all of them remains the same. So in the forward function, you take the attention. Here we mention the mask. This mask we create in the bottom. I'll show you how you create the mask. It's in the bottom. Here we mention we specify this particular mask. We get the output attention, and then we do this normalization and residual connection and send it to the transformer block. The transform decoder, same way how you create an encoder, we repeat this particular decoder block n number of times using module list, and then finally Each of them we do the same way. X is sent to the word embedding, position embedding, and then for each layer we take the output and send it as an input to the next layer. And then finally the out layer we send it to the softmax. Sorry, we first send it to a linear layer which calculates the logics. That will be sent to the softmax layer to calculate the probabilities. And then finally we get the final output values. So this output will be like, again, it should be 32 cross 100 ideally, because 100 is the number of vocab size, right? So for each batch, so it'll be, I think, 32 cross 10 cross 100, something like that. So for each batch, we for each output, the 100 is basically telling you, out of all the possible vocab size, what is the most likely token that will be predicted as output in this particular position. That is what that particular architecture's output size will look like. Okay, then transformer is nothing but combining both that encoder and decoder which you just created. This is the target mask. Again, torch already has triangular matrix command. Like I said, you don't have to worry about it. Torch.triangular matrix, torch. Once you mention what is the sizes you want, and it'll take care of the mask. So once you create the, this is a helper function to create target mask. Another function is to decode what you just created. So by decoding, it will basically convert into the final predictions of the sequence which are generated, right? It'll convert that particular output sentence what you created. So that is what the decoder decode does. So this is the final outputs you get. So let's test and see how it looks like. So let's say this is the source and this is the target, like input output, and this is the transformer. And if you print, these are all the architectures which you see of the model: transformer, encoder, then the embedding values, positional embedding values, then all the modules. We have 6 different transformer encoder blocks. Then the decoder starts. Again, there are 6 decoder blocks. And that's it. And the output of the size 2 cross 12 cross 11. And this is what the inference looks like. Again, we didn't train it yet. This is just a test. To train it, it will take time. And also, I'm not sure if it will support in a simple free GPU, which might be available. It will if you use smaller transformer, but typically it won't. You won't learn much information in these small transformers. You need bigger transformers. So yeah, this is how we create the entire transformer architecture. Again, I understand that there is a lot of content because we're creating from scratch. Don't worry, you don't have to create from scratch. PyTorch, there's something called as Hugging Face library also, if you're not aware of it. They actually create very good abstractions, just like CNN, right? Like nn.cnn. Just do that and you can do all the CNNs. Almost to that level of abstractions they create even for transformers. So you don't have to manually write everything from scratch, but it's a very good exercise to understand how these all layers interact with each other, the shapes, the dimensions of QKV, everything. It will be very helpful if you can go through all of this. But in actual production or deployment, you don't have to write everything from scratch. You can use existing libraries to create much more efficient transformers. Okay, any doubts in the overall code or any other questions which we discussed? Okay, if not, let me stop the recording for now.